So welcome to the seventh lecture of Mathematics for Minor Finance. So today we're going to talk about matrices and matrix operations. Basically, this is going to be an introduction into the topic of matrices. So not going into too much detail, but it is helpful to have basically the background that we're going to cover today to use in courses in your finance master, like portfolio theory, where it is actually extensively used. So then you know where to turn to. So what's the agenda for today? So first I'll give a little introduction into what matrices actually are. Then this large part devoted to matrix operations. So it turns out that when we have a couple of matrices, we can actually add them up and we can multiply them. So we'll discuss in some detail how that works. Then we'll go to the inverse of a matrix and the transpose, and after having covered all of that, we'll wrap up with the course, because this is the final lecture that we are doing today. So what are matrices? So to introduce those, let's consider once again a system of linear equations. So here you have one like 2x1 plus 5x2 equals 4 and 3x1 plus 7x2 equals 10. So we've encountered that. So this is called a system of two linear equations. So linear because the two variables, the x1 and the x2 that we want to solve, occur in a linear fashion in either equation. So no squares or no x1 times x2 parts in these equations, two linear equations. So this is a system, and typically you would like to solve that, right? And we've basically dealt with how to do that. We have covered some techniques of doing that, like eliminating or substituting one variable for the other. And then we could figure out basically what is x1 and what's x2 that are going to solve these two equations. So, of course, we have such systems of equations many times, both in economics and in finance. And in addition, actually, it's often not only limited to these two equations, but often we have like lots of equations, perhaps even 100 equations with 100 variables. And then you can understand that it might be sort of, at least a lot of work to solve those by hand. So there's actually the question of are there sort of general techniques that there might be that we can use actually to solve these equations also when they are a bit bigger than just 2 by 2. So some examples of that you will see in the courses that you'll take. So as I just mentioned, portfolio theory, so in the optimization of a portfolio of stocks. So we looked at the question, well, what happens if we have 3 stocks last time? But in general, is many more than 3 stocks. There might be 100 or even 1,000 different stocks. So the question of portfolio optimization requires first order conditions on 100 or 1,000 equations at the same time in order to find what weight do we have to give each stock in this final portfolio. So that's a big, computationally at least, that's a big question. So it's nice to actually have some general technique that allows us to look at such large scale examples in a sort of systematic fashion. Also in econometrics, you'll do an econometric course soon, actually. So what we typically want to do in econometrics, one thing we want to do is regression, linear regression often. So basically that means fitting some line through a lot of points. So it means finding some variables like the intercept and different slopes in order to fit a line as closely as possible to a number of observations, the x and y's. So it turns out that this is also related to the least squares, as it's called, ordinary least squares regression, for instance, OLS, requires solving a lot of first order conditions, essentially, optimization conditions. So again, it's going to be useful to express these conditions in a way that's sort of amenable to analysis with lots of variables. So if you have lots of points and lots of parameters that we want to estimate, then this is called for. Also in macroeconomics, of course, the simplest macroeconomic models would only have, say, capital and labor, but more realistic ones actually have many more variables in there. And in order to solve these macro models, you would also need to solve first order conditions for many different variables. And same with microeconomics. If you have a market with lots of goods, lots of different prices, in order to optimize welfare, to find prices, basically the optimal prices, you will again have to solve a lot of different first order conditions. So how can we conveniently deal with such larger systems of equations? That should be a question that should be of interest to us. So let me write such a system of equation in a very general form. So this is a linear equation. So the variables or the unknowns that we want to solve for are called x1 until xn. So the n unknowns. And suppose we have m different equations. So I wrote those m different equations over here. So there they are. This is the first equation, the second equation, etc. until the mth equation. And in each of these equations, they will involve all these different n different variables, x1, x2, etc. until xn. And typically they will have the form of some number. Let me call that, just for notation's sake, a11 times the first variable, some second number, let me call that a12 times the second number, etc., plus, plus, plus. Final number times some parameter a1n equals some new number b1. And similarly for the second equation, second number a21, again some number times our first variable, some number times the second variable, until some number times the final variable, the nth one, equals some second number b2, etc. until we have reached the mth equation, the final equation, which again has these n different terms over here, one for each different variable, the x1 until the xn, equaling some bn. So this is just, recall here we had just the 2 by 2 equation, so here m and n would have been 2. Here we have generalized this to n different numbers, it's not just x1 and x2, but it might be until x10 or until x100 or whatever you wish. And there might, instead of 2 equations, there might be lots of different equations that you need to solve. So now this is just such a system. So what we might first note here is just some notational thing. It is going to turn out to useful to actually collect all these different coefficients. So the a11, the a12, up till the a1n, and down here the a21, a22, up till a2n, etc. until am1, am2, etc. until amn, to collect them into basically this block describing these m times n different elements of this form a, I, j essentially. And we call this block with these brackets around them, we call this the coefficient matrix related to this system of equations. So some further jargon here, we call these things rows, right? There are m different rows here. One, second row, these horizontal lines are the rows, right? So there are m different horizontal lines, so m different rows in this coefficient matrix, bold A. And there are n different columns, so one for each variable essentially. So this is the first column, this second vertical stack is the second column, until the final, the nth vertical stack, that's the nth column. So the m rows and n columns, and in total are basically therefore m times n different elements that are basically these different a's that you see in these equations. Okay, so that's just a name, right? Now the nice thing is that we can do some computations with these matrices, but before that let me just review a little bit more notation actually. So if you have here this matrix of coefficient, this coefficient matrix, so the a11 until amn. So if the m and the n are the same, so the number of rows, the rows where these horizontal lines basically, and the number of columns, the vertical stacks, are the same, then we call a square matrix. So for instance, this one is a square matrix because it has 2 rows and 2 columns. If we just have one row, so basically m equals 1, so we just have one of these lines here, or here's an example actually, and a matrix 4, 10, 8, but that's the first row and there are no further rows. We call this actually a vector, a row vector. So m equals 1, this is going to be a row vector. It has n columns, right? So very short columns, but still three columns all the same. 1, 2, 3. Each column now just consists of this one element. So this is called a row vector. And similarly, we also have a column vector, and that happens if it's just one column. So this is this would be a matrix with 3 rows with just one column. We call this actually a column vector. That's again just a name. So the nice thing with these matrices, well, this was just a definition, but now we can go on and talk about some operations that we can do with these matrices. And when we have discovered or discussed those operations, it turns out that's going to be very helpful in solving, for instance, the types of multiple equation systems that I just talked about in a systematic way. So let's go on to talk about matrix operations next.